Hello, everyone. I'm Arnab, and today we'll be talking about scheduler and sharding considerations for network efficiency. We will also be joined by my colleague Weiwei shortly. So before we get into the talk, a little bit of background. I've been at Meta for 6.5 years, and most of my time here has been focused on AI infrastructure. Within this context, I've been focusing mostly on MAST, which is the ML training scheduler for all GPU training at Meta. There was a paper that we published recently about MAST in OSDI 2024. So if you want more details, definitely give that paper a read. So within this context, here at AI infrastructure at Meta, we've been focused on large-scale training and the transition to AGI. So let's talk about AGI. So from an industry perspective, there's a big push today to get towards AGI, or artificial general intelligence. And here at Meta, it's no different. There's a huge focus on getting to AGI via our Llama models. In general, we've found that more compute leads to better model performance. And here at Meta, we have thus been investing in increasing the size of our large-scale training clusters. So with that being said, last year, we built a 24,000 GPU network for training ML models at scale. We ran into a number of scalability and latency problems when designing a network of this size. Specifically, at 24K scale and beyond, scheduling and sharding considerations for the model become more important due to the cost of network hops between GPUs on a network. The cost of doing nothing here is that training performance is impacted, which is undesirable. So for Llama 3, training took months of time to complete. And with the efficiency improvements that we've made here, we reduced the total training time by months, thus greatly reducing the cost of running training on several thousands of GPUs. With careful sharding and network configuration, Llama 3 achieved a GPU utilization of 40% at large scale. This talk will be broken up into two major subsections. In the first section, Weiwei will be talking about parallelism techniques and model network co-design. In the second part of the talk, I will be talking about scheduling considerations at scale. With that, I will hand it off to Weiwei.
Thanks, Arnab, for the introduction. I'm Weiwei from AI System and the Co-Design team at Meta. I work on model co-design and training efficiency for Llama and the recommendation models. I will explain what is parallelism and why network config and the scheduling are critical to parallelisms. So first, what is parallelism and why we need parallelism? To train a model, we need to fit the model into hardware memory. For example, Llama 3 for 5V model will need over 700 terabytes of memory. However, of H100, each only has 80 gigabytes of memory. So we need to split the model over 16K GPUs, with each GPU using over 60 gigabytes of memory. So parallelism is to shard the model to fit into GPUs, and parallelism need to minimize the communication between GPUs. There are many different types of parallelisms. They have different ways of sharding the model, and they will introduce different communication between GPUs. I will introduce two of the parallelisms and explain their implication on network and scheduling. The first one is called fully sharded data parallelism. Suppose we have a matrix multiplication with inputs X, weight matrix W, and output Y. And we have two GPUs. FSDP will split the weight matrix into two shards, W1 and W2, and put the two shards onto two GPUs. Then, before the computation of the matrix, we will need to first gather all the weights from all GPUs. Now we have the complete weight on each GPU. We also need to shard the input X and get the corresponding output Y. After computation, we release the weight back to its GPU. So each GPU just keep a shard of the weight. Computation and the communication will happen together. So when the compute stream is working on the computation of layer I, the communications stream can start prefetching the weight matrix of layer I plus 1. So we can see that the communication of weight matrix can be easily hidden by the computation through prefetching. In contrast, tensor parallelism will always need to keep the weight matrix sharded onto different GPUs. But we will need to gather the output Y. There will be multiple such computations in each model layer, and the computation will need to depend on the previous computation's output. So TP will introduce multiple heavy communication, and these communication are hard to be hidden by computation. There are many other parallelisms. These are the commonly used ones. So the choice of parallelism combination depends on our model and network. The goal is to have the model fit into hardware and have minimal overhead from communication. For example, if FSDP, the altogether of the weights, becomes the bottleneck, we will need to use TP to reduce the amount of GPUs in each FSDP communication group. In this summary, TP has the largest communication data size, and it is hard to hide its communication by computation. So TP has the lowest tolerance for network. TP will need to use the highest bandwidth network. CP, they are medium hard to hide their communication by computation. PP and FSDP, they are easy to hide their communication. Thus, they have high tolerance for slow network. It is important for us to make sure that each parallelism makes the best utilization of network bandwidth. In Llama 3, we use network-aware parallelism. We ordered the 4 dimension of parallelisms carefully for the best utilization of network. We put TP at the innermost, which is within a rack and has the highest network bandwidth. We put PP the second outermost and try to avoid cross-AI zone PP communication. We put DP, which is FSDP, the outermost, and it will be cross-AI zone. Then what will happen if we don't place parallelisms properly? Improper placement will lead to slow communication in a group of GPUs. Suppose if we put 2 TP GPUs across AI zone, then the communication in this TP group will be super slow. Since there will be a synchronization point between all the GPUs at the end of each iteration, any slow GPU group will slow down the whole training. Now we know that network is critical for parallelism. I will hand over to Arnab, and he will talk about how we schedule GPUs to satisfy network requirements.
Thank you, Weiwei. We will now talk about scheduling considerations at scale for ML training. So earlier, we had talked about how we had built a 24K GPU network last year at Meta. The cost of internet communication between GPUs with such a large network goes up the further away in the network topology the GPUs are located. For example, GPUs that are located on the same rack will communicate with each other a lot faster than GPUs that are, for example, located in different buildings. So specifically, even RDMA-backed AI zone networks have to obey certain laws of physics. So nodes in the same rack have the fastest communication, while nodes that are further away from each other, for example, in separate AI zones, will have higher communication overhead. And the impact of this is encapsulated by a metric that we call RTT, or round trip time. And increased RTT would mean that you would have a slowdown in training, which is undesirable. Thus, one goal we have here in the scheduler is to minimize communication between nodes at higher levels in the network topology. How do we do this? We do this via the notion of ranks. A rank is simply an identifier or index in a process list for an ML training job with each process running on a different GPUs. And the reason we have ranks is that large training models cannot fit onto a single GPU, and thus are broken up into ranks. Ranks with closer indices communicate more often, and we thus want to make sure that they are topologically closer in terms of network. How do we do this? How do we ensure that ranks that are closer to each other are also topologically closer? We do this via the notion of rank assignment. So rank assignment simply means assigning ranks to different GPU hosts. In order to do this, we topologically sort the hosts so that network hops between consecutive ranks are minimized. We have implemented this for MAST, and this has been rolled out, and this is what is being used right now to enable cross-zone communication. So what happens if we don't do this? This diagram here shows you a bad example of rank assignment. So here in this example, we have two different AI zones, and we have 4 GPU hosts, 2 in the first AI zone and 2 in the second AI zone. And since we haven't worried about rank assignment, here we can see that GPU hosts 1 and 2 are making several hops in order to communicate with GPU hosts 3 and 4. Specifically, we can see that GPU host 2 is talking to GPU host 3, and GPU host 1 is talking to GPU host 4, but there's a lot of back and forth communication. And this can increase a number of slow communication channels and latency-sensitive parallelism techniques, such as tensor parallel, thus leading to bad performance. So how do we ensure good rank assignment? In order to place hosts with a higher communication rate closer to each other, the scheduler needs to know about the network topology information for each host. So every GPU host on the backend network has an associated rack, row, and AI zone ID. And MAST, which is the scheduler, knows about this rack, row, and AI zone ID per host so that it can sort the hosts topologically while figuring out how to allocate new incoming jobs. And this, in turn, lets the scheduling system get the best ML training performance. So if we did what we described in the previous slide, this is how good rank assignment would look. So good rank assignment ensures that we minimize the number of slow communication channels, thus speeding up the latency-sensitive parallelism techniques. So here in this diagram, we can see that via good rank assignment now, GPU host 1 is only talking to GPU host 4, and GPU host 2 is only talking to GPU host 3, and we have thus minimized the amount of cross-zone hops, and thus we have better ML training performance. Unfortunately, at large scale, at very large scale, rank assignment by itself is not sufficient. This means that we could still have the various different parallelism techniques that we were talking about earlier see performance regressions. So specifically, we have tensor parallel, data parallel, model parallel, and pipeline parallel. And we earlier asserted that tensor parallel should not go outside of racks, and then model parallel and pipeline parallel should not go outside of zones, and only data parallel can go outside of zones and across buildings. So the scheduling system doesn't understand these parallelism techniques. Instead, MAST is provided allocation constraints per network affinity scope. For example, allocate in multiples of 128 per building, or allocate in multiples of 2 per rack. MAST has to honor these constraints at job allocation time, and the training application will then know that, hey, I have these 2 hosts on the same rack, and thus I want to run tensor parallel only amongst these 2 hosts, and so on. So thus, by ensuring that the allocation constraints are honored, we will have the intended effect, and the various parallelism techniques can run well, and then we have the best ML training performance. In terms of topology-aware scheduling, there's also a consideration with buffers. Specifically, because of this topological awareness in scheduling, we have increased buffer requirements for MAST jobs. For example, if we have a topological constraint of 2 hosts allocated per rack, with the rack having 2 GPU hosts, and we have 50 racks allocated, and all 50 racks lose 1 host, then we would need an additional 50 racks of hosts available to reallocate the job if all 50 racks lose one host at runtime. Thus, with topology-aware scheduling, we need a dedicated buffer of spare hosts that is also pre-allocated according to the same topological constraints to ensure sufficient capacity at runtime for the job to run to completion. There are also other scheduling considerations that we have at scale, such as scheduling overhead, fault tolerance, and fault tolerance. So scheduling overhead here means, for example, what is the amount of time that's taken from the time that the first trainer crashes to the time that the training application re-enters main. And because the probability of host failure goes up with the size of the job, this is super important. And we've been working on techniques to optimize that. With fault tolerance, we're looking to see if there are different parts of the training application that can be resilient to partial failure. So for example, at runtime, if some parts of the model go down due to capacity going down or other types of failures, can the rest of the model still continue to train? And these problem areas all overlap. So scheduling overhead, network overhead, and fault tolerance all overlap, and we cannot reason about them in isolation. So with that, we spoke about all of the different scheduling considerations at scale as we built out these large-scale networks at Meta. And now I will hand it off to Weiwei for the wrap-up. Thank you.
Thanks, Arnab, for the great talk. Now we understand that it is super challenging for both parallelism and scheduling at large scale. Then what we can do to get the best throughput from existing infra and model? One way for this is to do infra and model co-design. So in the past, we built hardware and infra based on the trend of the model. When the model gets bigger and bigger, we will need faster and larger GPUs, and we will also need faster network. However, it can take years to build new hardware and infra. So models also need to fit to the existing infra and hardware. For example, if we have less GPUs connected with scale-up network, this infra will favor smaller model and a combination of TP and PP for parallelisms. But if we have more GPU connected with scale-up network, we can design wider models, and the new model architecture may be more favored in this setup. And we can design hardware and infra-friendly model with both good model quality and high training efficiency. To do this, we can build a model that can predict the training throughput given certain model, certain hardware, and the training setting. So infra, such as network, scheduling, and so on, they are critical factors to the next generation of model. The takeaways for this talk are, first, network topology-aware parallelism and topology-aware scheduling help ensure training efficiency. As Arnab mentioned at the beginning, for Llama 3, with careful tuning of all these things, we achieved over 40% of GPU utilization at large scale. Also, this consideration allows for large-scale training with communication across higher network scopes. Topological sorting ensures scheduling layer is not aware of parallelism abstractions. And lastly, other scheduling considerations in addition to network overhead mean that we need to consider these problems together. That's all for this talk. Thank you all for your attention.